was wondering where you were.
Wow, skate bar.
This is huge.
Yeah, that's so big.
Wait, is that electric?
Yeah.
After class, can I try it? Oh, yeah!
Wow.
Oh,
Exciting, huh?
exciting!
Don't fall down.
Sweet man.
Yesterday you got it.
Oh.
Oh, I'm so excited. So excited now. Where did you buy it?
Online.
Online. From Ireland or the UK?
From USA.
Oh, excuse me.
1 month.
1 month?
Yeah, I ordered it in Christmas.
Ah. Special price?
No.
Like sale price?
No.
No.
800.
Is it fast?
Yes. So fast.
You really?
Yeah.
Top speed?
32 kilometers.
That's fast because the speed limit in the city centre is 30.
Oh, really?
Yeah. So that's 2 kilometers per hour more than the cars,
Yeah.
which is fast. Okay. Right. Let's have a look. A bar magnet lies horizontally on some paper, which is also horizontal. A magnet lies on the y-axis with the north. Come in. Yes. Problems?
Good morning.
Good morning.
My goodness, it's the best attending class.
Look to your left.
Wow.
That is an electric skateboard.
Does that have to be registered?
I don't think so.
Is it?
KJ's.
Wow,
And
that's amazing.
he said I can try it after class. Isn't this so exciting?
What time is this class here?
It's a double class.
Okay.
I don't know.
I might have to find a
Principal might want to go. Would that be inappropriate in front of agents?
Yeah.
Yeah. So what you need? You know how?
The silver laptop, I'm not registered on it.
Uh-oh.
Yeah.
Okay.
Are you able to log into it?
If I... Oh dear. Whose username is on it at the moment? Nobody's?
Neil is top it up.
I don't know. You see, if I've never used it.
Oh, there's probably aren't. I don't remember.
We do this?
Okay.
Okay.
I don't have that question.
Do you have this model? No. Do you have this model? No.
Yeah, we have it.
No. This is a good and serious system.
Yeah, that was down there.
She said we haven't moved it. So I never
It
tried.
is not.
So this was why I got
I didn't want to do that.
I did want to do that.
So sad.
Electric field.
I do not have that. This is the newest one. What? Not the youngest one. Half of it is dark.
Oh, yes. God, we haven't moved it. We haven't moved it.
Oh, we have the model. Okay, no, do we have the question?
Yeah, that has to.
Okay, no reason for doing that.
Do you have assessment support later?
I asked Lorraine. They didn't reply.
What did you say?
I just sent the email.
Oh man, we do have it, but I can't go back home at time plans.
But you can leave here for us.
Yeah, I know that.
I mean, you can stay here.
We have computer in our house.
What do you?
No, I mean 2 hours คนละครับกันเอาว่าเอาตัวว้าวback
Go to computer lab up there. We have.
We can access the computer, maybe.
Yeah.
Can we?
Yeah.
Really?
Use the power.
Your
I don't
serial
know how to
number
use
is Irish, and then your.
I don't have the number yet.
Why?
Until now.
I mean, if you don't have card, your serial number is in the US book. But
真的我 I just
but
use
I got first,
Saturday
then
and Sunday
take card. Oh, you can go to his room and then use
Yeah.
his computer.
No, no. I want to use
I have
mine.
some secret.
What is it?
I fixed the principal's laptop, and look what I got as reward.
We have.
就是按照他就是这些。啊。
What? We have 3 questions.
Hang on, I'm doing this now. So, what?
Yeah.
Do we? Okay, we'll do 3. Okay. I'll do this one first, and then go to the next one. So, I said the magnet lies this way, north and south, and an electron moves along the x-axis. So there's a little electron, the electron moves this way, and my question is, what direction is the force? So, which rule is this, left or right? B, let me see, this is going this way, so the B is actually down, isn't it? Because it goes from north to south. Yeah, so that the field lines are pointing down. What way is the current? To the left or to the right? To the left. Because the electron is a negative, so the current is to the left. So is the force towards me? Towards me, or rather out of the page. Out of the page. It's like this. I thought out. If I'm looking at this, this is the F. No, sorry, what am I saying? This is the B. This is the I. So it's out. From me looking at it, it's out. For you looking at it, it'll be this way. Yeah. Yeah. Who profoundly disagrees with me? You disagree? Really disagree?
I don't agree.
Is it just Monica? Because I'll continue with
Do
just
we
Monica.
point towards N or towards S?
No, you point in the direction of the field. And which way is the field pointed for the magnet? It's from north to south. The field line. The B is the field line direction. Not the magnet, not the physical magnet's direction. The field line's direction.
Okay. Inside.
What is this like? Are you like flipping me off or something? Is this like some kind of profanity? Like, hey Stephen!
It's inside.
It's like that.
It's inside.
Watch! Tell me, hey, watch. B, true? Which way is the B?
Down.
Up or down? Down. Okay, I. Left or to the right?
Right.
Left. This is an electron. Remember, if the electron moves right, we say the current moves left. Oh, look at all your confused little faces.
I get deeper away, you know. Like this.
Okay, can I go on to number 2? I thought this would be a quick question. A magnet has a magnetic flux of 400 milliwebers. Over a square region of length 2 centimeters. What is the flux density? Okay, what's the formula here? What's the formula here?
V equals plus A.
What's that, please?
1,000.
Exactly 1,000? So 1 kilo Tesla. Yeah. Alright, that's fine, isn't it? Okay. 3. An electron moves perpendicular to magnetic field of flux density 500 millitesla. What is the force on the electron if its speed is 0.01 c? Okay, so which formula do I need here? Yeah. Do I know the Q? I do. It's an electron.
Yeah.
Do I know the V? I do. It's 0.01 times the speed of light. And do I know the B? 0.5. So I just hit this in. You've done this already, Monica. What did you get?
2.403
Minus 13. Okay. Quite small. It's because the E is so small. Number 4? Yeah. Okay. Now, this one's a bit tricky. I wonder if anybody got number 4. You think you got it? Did you get it right? Can we actually, I kind of like this as a profanity. Could we actually use this in physics class? You know, if somebody's annoying, you can just go, hey, right hand rule. No? I would like it to catch on. No? Okay. Right, 4. A particle moves with a charge of -2. It moves in a magnetic field at a speed of 0.05 c at a direction perpendicular to the field with flux density at that. And it causes it to move in a circle. Why might it cause it to move in a circle? Well, let's just try and draw a picture, okay? So, the electron is moving, wants to move this way. So, which way is the current moving? The left. Now, we said the force is perpendicular. It doesn't really matter. Do you want me to draw the force perpendicular this way or perpendicular this way? Up or in? Which would you prefer me to draw? Up? Okay. So, I meant the B. The B is up. Yeah. So, which way is the force? Well, let's see. B, I. So the force is into the page.
What?
B, this way.
It's fine.
I, this way. So, because that's an electron. So the I is that way. So the force is into the page. Yeah? What will happen is that the force will act in and actually cause the electron to move in a circle. And I want to know, what is the radius here? The electron, guys, can you look at my hand? The electron will come along and when it enters the field, it will move into the page in a circle. I want to know what is the radius of this circle. So, what formula could I use here to get this started? Yeah, you could say A equals V squared over R. This is circular motion. MA equals mv squared over R. That's equal to F. But F also equals Q VB. So therefore, mv squared over R equals QVB. So R, which is what I want, is mv squared over QVB. The v's cancel, and I'm left with mv over QB. Okay, so firstly, what is the number for an electron? Whoops. Is it 1 or 3? 3, isn't it? Yeah, the mass. How fast is this moving? I think I said 5% the speed of light. Can you check your calculator lid? Which constant is C0, the speed of light? C0 is on the calculator. 28? Okay, what is the charge of this? I think I said it's 2 electrons, didn't I? Which is 23. And how strong is the magnetic field? 750 milli. So the radius is exactly this much. Let's make that into micros. 56.8. Now that feels wrong. But is that what you got? Oh, sorry. It's not an electron's mass. I give you the mass. I'm sorry. Okay, so it was wrong of me to put this here. I should have put 10 to the power of minus 25. Okay. Yeah, that's better. 6.24 meters. Is that what you got? Yeah, good job. Is that what you got?
No.
Better luck next time. Got that? Yeah. This actually is a very important experiment, because what you can do here is you have this formula. Let me show you here. R equals mv over qb. Now I could rewrite this a little bit. I could bring the b up and bring the v down, and that's m over q. And actually, if you did this experiment, it's easy to know what the R is, because you can measure it. You can see where the electron hits the screen, and you can measure the R. Could you know the B? Yeah. And you can actually know the V, because the speed of the electron, if you fired it, you can know the V that you fire it at. And I can show you that I can show you how to do that, because perhaps we fired this electron by using an electric field. You have the formula that the kinetic energy here equals the potential energy here. What's the formula for potential energy? It was what was it? QED. QV. Yeah, that was it. Yeah. Wasn't it? If it's in a field. Anyways, my point is, you could know the V, or even know the V in terms of Q. So all of these are known. Now, that means you could know what this ratio is. So you could say M over Q, you could know this. But last week we did an experiment where the oil drop experiment I talked about, where you could measure the Q. You remember I said about the oil drop experiment, where you have all your Q's, and if all the Q's are some number multiplied by n, you could figure out what the Q is. So then you can know the Q. But as soon as you know the Q, you can know the M. In other words, this experiment gives you what's called the mass to charge ratio, or charge to mass ratio. Something perhaps you talked about in chemistry? Yeah, you did this in chemistry? This particular equipment. What is it? Is it called a spectrometer? A spectrometer? Yeah. So this is how you can measure something tiny like the mass of an electron. You can measure its mass to charge ratio and then measure its charge, which I just think is very nice. These two experiments work very nicely together to get something which is quite difficult to get. You obviously can't weigh an electron. It's a bit hard, because when you put on the weighing scales, you drop it so easily because it's so small. Yeah. Right. What's the next one that I skipped that I need to look at? Well, sorry, you said there's 3 to do, so I must have skipped over one, did I? Oh, I have these 2. Oh, but I wasn't going to... Well, I could do this one today. I was going to do this one and 7 together in another one. Anyways, we'll do 5 now. This is lecture 5 then. Yeah. Okay, copper wire carries 4 amps of current. The copper runs through a magnetic field so that the copper is perpendicular to the field. The copper is 40 centimeters long and the field has a flux density of 6. What is the force acting on the copper? Which formula do I need here? I just need the good old VIL. Do I know the B? I do indeed. It's 6. Do I know the I?
Yeah.
I do. And do I know the L? 6. Isn't it? The B? 6?
Yeah.
4 and 0.4. What's this? Did you have this? 9.6 newtons. Thank you. Okay, 2. Oh, sorry, no, there's a B part. The B part is just if you have an angle. So the angle would just be 9.6 times. Is it cos or sine? I thought it was sine for this one. Sine 70. Alright, so this should be, what's it, like 8? What's the answer here? Oh, okay, that's higher than I thought. No, that sounds fine. That sounds fine. Okay. Number 2. A DC motor is used to turn a wheel. A current of 2 amps runs through the DC motor and the magnet has a flux density of 6 and the wire runs 2,000 times around a square of length 30. The side of the square is attached to a wheel. What is the torque of the wheel? So what's the turning force of the wheel provided by the DC motor? Well, what's that? I-ban for the torque. Do we know the I? We do. Do we know the B? We do. Do we know the A? Yep, we do. And do we know the N? We do. So we should get a pretty big turning force here. What's the torque? What is it? 600? Isn't it 0.3? Yeah. Yeah, if you could type that in, please. You have the answer. What is it?
250.
Ah, too easy.
This exam level.
Section A only, like a maybe a 3-mark section A question.
They give you all of them.
No, it's all right, isn't it? Okay. A coil is wrapped around an iron rod of radius 10, a total of 200 times from bottom to top. A magnetic field runs from the top to the bottom of the iron. Okay, I better draw this now. Right, I have some iron. Whoa! Okay, and this is 3 Tesla, and this runs around 200 times, and we know that this radius is 10 centimeters, and this length here is, do we know? Oh, we don't know. I guess we don't need to know. What is the flux linkage, which means the total flux? So the magnetic field cuts how many circles? 200 circles. So the total flux linkage will be, 200 times the flux. Now, we need to use this formula for the flux. The flux is VA. So that's 3 times pi or squared. Alright, so what's that, please? Do you have it, KJ? 0.71. Oh, it's fair enough, it's the principal. Who's calling me? Do I want to answer? No. It's about my car. Thank you, KJ and Andrew.
6, 5.
Hmm?
6, 5.
That's small.
But why?
18.84.
8.
Correct.
1 is 8.5.
188.
0.85.
1.
8. 0.85. Point.
8.
8, 5, 5.
Webers.
Isn't it 2000 or 200?
Oh.
It is 200.
Oh.
Do I want to use milliwebers? Nah. What? Using this slide?
Maybe you have different slots.
That's kind of like spooky, like somebody came in during the night and changed the numbers on my slides. Anyways, no matter, everything's the same except the numbers are strangely different. That is weird. That's very weird. No matter, anyways. The last part is if the angle is 20 degrees. Can you multiply this by cos 20?
Yes.
What do you get?
17.7.
17.7 Webers. Okay. Can we look at the induction one now? Yeah. Okay. Come on, catch up. There we go. How do we do on this one? Yeah? Ah, the first one. So, you all saw my trick. I was trying to confuse you, make you think really hard about which part of the story do you actually have the current. Is it when you turn the manhole or when you lift the manhole? When you lift it. Very good. Okay. So, Faraday said that the EMF, the voltage, I won't care about the minus, and the N is 1, so it's just going to be this. What's the time here? 2 seconds. Now, be a bit careful here. What is the change in the flux? Well, what's changing here, the B or the A? The A is changing. So the B stays the same, and it's the change in the area. What is the B? It's 0. So it would be 0.035 if I divide by 2 times the change in the area. And how is the area changing? Well, you're drawing a rectangle moving up through space. Thickness 2.5 and half a meter. Times another half. So I should get a tiny voltage. What do I get here? Oh my goodness, 0.43. Not even 1 microvolt. Like half a microvolt. Nanovolts. It's because the magnetic field is so weak and the distance is so small.
So it's not pi r squared.
No.
So model clash like this one is kind of different.
I know I changed it a little bit. I made it a bit harder.
In model?
No, this one. Because this one here, I'm trying to make you think about when you get the voltage. Okay. I have to update those Moodle links. 2. You on to 2? Is that okay? Yep. Now this one is quite interesting. A 2 meter horizontal pipe is dropped from a height of 100 meters. What is the induced EMF? So you have a 2 meters of pipe, and it falls a distance of 100 meters. So again, I just care about there's n is 1, and I don't care about the minus right now. So what's changing here, the B or the A? The A again. Now I do need to say that we are making a little bit of an approximation here, because this change in the area over the time, the area is not changing at a uniform rate, because at the beginning the area will increase slowly, and then later you get more area per second. So actually this is not a constant, it's changing. But it's okay for these questions. We can imagine that the area is increasing steadily, even though we know it's not increasing steadily. So the B we know, the A we know, but the T, do we know?
1 second.
How can we get the T? Yeah, so did you get the T out here? What did you get, Monica? Okay. So, again, should be pretty small, but not as small as the manhole cover. What did you get? It's pretty big compared to the last answer. Yeah. Continue. Okay. Number 3. A copper wire is wrapped around in a circular loop of radius 5 a total of 100 times around a magnet. So you've got a magnet, and you take a wire and you wrap it around 100 times, and this is 5 Tesla. No, sorry, it's 2 Tesla. And the radius here is 5 centimeters. Good, okay. And then what you do is you pull the magnet out. So you quickly pull the magnet out over a small time of 1/4 of a second. Yeah. Okay, so the E here is going to be minus, so we won't care about the minus, 100 over 0.25. And what's changing here, the B or the A? The B is changing, so the A stays the same. The A is going to be pi r squared. And the B changes. Now, how does the B change? It goes from what to what? It goes from 0 to 2. So it'll be 0 minus 2. Or 2 minus 0. Well, really it's 0 minus 2. The reason for that is because you're losing the magnetic field. You go from having a magnetic field to not having one, so the change is a negative. It goes from 2 to 0. Yeah, but the delta B is minus 2 Tesla, because you go from 2 to 0. You lose 2. Yeah. But we don't care about the minus anyways. I just want to know the size. Alright, so what do we get here? That's pretty big. You could power a calculator with that easily. In fact, you could power a efficient home light bulb, because I have LED lights in my house, and they run off of a tiny voltage of like 4 volts. They're very efficient, but they're just as bright as normal light bulbs. So yeah, you could actually light up a room with this 6 volts. Yeah. Average? We kind of are using average, Jerry, because this is the change and this is the time. So it's like we're using an average, but instead of dividing by 2, we divide by the time, because we care about how quickly it changes. Yeah. That 6.28 is an average voltage. For as I move the magnet out, for some time it will be less than 6, and for sometimes it will be more than 6. It's on average 6 as I move it out. It's just an average. Okay, this I think is okay. Can we go to the next one now? Number 4 is my favourite. The reason it's my favourite is because it's a real example. You make an AC generator and you would like to know what voltage you will have. Okay, so you have your N, you have your S, and at the beginning it's like this, and then later, small time later, it's now like this. So it's spinning this way. So the first part is, what is the total flux linkage when the plane is vertical? For the first one. Well, do we know the N? We do. It's 10. Yeah, 10 windings. Yeah. Now, this will be B. Do we know the B? 5 Tesla. Do we know the A? We do. It's 0.2 squared.
Yes.
It's 20 by 20 square. Did you have 0.3 by 0.2? Because I think that's what it said on Moodle. It's okay? Alright. Now, here's the problem though. Is this in the right direction? Well, let's use the right hand rule. Okay. The F is which direction here? If I'm turning this wheel, which way is the F? Well, the F's going to have to be like this way, isn't it? If I want to turn the wheel. Or we could look at the bottom, we could look at it this way. But let's just look at the top first. The F is that way. Okay. F is to the right. To the left. Which way is the B? The same way as F. And so we have a problem. We can't be in the same direction. So in fact, this will equal 0 Webers. And if you want, it's kind of like I have a cos 90 degrees at the end. Because it's at the wrong angle. It should be perpendicular, where instead the F and the magnetic field, can you see they're parallel? We can't have them parallel, they need to be perpendicular. So the first one is 0 Webers. But for the second one, it's 10, 5, 0.2 squared cos 0 degrees. It's fine now. What do we get here? Someone can calculate that for me, please.
Almost, yeah.
2 Webers. Okay, super. C. What is this? Now, tell me why I don't need to write the N here. I've already included it here. In other words, the N is already inside my calculation here. So if this goes from 2 Webers to 0 Webers, but what's the time? Well, in the question I said it has a frequency of 50 Hertz. Yeah, so that's, the 50 is 1 over t, so the t is 1 over 50. No, not 1 over 50. Why is it not 0.02? It's not 0.02, why not? Oh, come on, somebody must see why it's not 0.02?
Oh, it's 150.
Yes!
So it's times 2.
No! Ah!
Divide by 2.
No! Divide by 4! Because it's only rotated a quarter of a circle.
That's why full all.
Oh, how?
This is the time for one. Here's it is. Look, this is the time for it to go around once.
Yeah.
Look at the bottom of the pen. Look at the bottom. The time to do this. Okay, that's not what it's doing. All right, it's only going like this a quarter of the time. You know, if it takes 4 seconds to do this, then it only takes 1 second to do this. So I need to divide this by 4. So this will be 8 over 0.02. What's that? Should be pretty dang big. Is it? Well, this is 50 times 8. 400, yeah. 400 volts. But I kind of was being a little bit sneaky at the end. I asked for the maximum voltage, and this here is actually just the average voltage. Yeah, multiplied by root 2, isn't it?
Yeah.
It's just lots of like hours we have to write it down.
I'm too lazy to. I'm leaving it like this. In the exam, the decimal is better, please. Yeah. Yeah. It's okay. Yeah. Yeah, it's a little bit tricky, but I don't think there's too much maths in it. Okay, so what we'll do, what's the next lesson here? Yeah, okay. So we'll take a break for a couple of minutes and then start the next physics lesson. After lunch today, we have a double maths, don't we?
Yeah.
Is the maths class today the last maths class of the week?
Yeah.
It is.
Yeah.
So that means in the second maths class we'll have a tutorial. Okay, take. Huh?
One tutorial.
One tutorial today.